So in this part of the lecture we have reached to Lie groups. So and we will discuss about Lie groups. Well, as the name suggests, we have a group, but there is a name in front of it called as Lie. So Lie group is a special kind of group and that has some special properties. So this Norwegian mathematician called as Sophus Lie, so he invented an analysis for group, and this analysis called as a Lie analysis, and only those groups that satisfy this Lie analysis are called as Lie. So the idea is we have a group and we have a certain kinds of groups that agree with something called as Lie analysis. So you can do Lie analysis with those groups, and all those groups for which Lie analysis is possible, we call them Lie group. Now, of course, Lie groups are continuous groups, no doubt on that, and we just learned what continuous groups are. And of course, Lie groups can be symmetry groups, no doubt on that. For example, SO2 that we studied till now is a beautiful example of a Lie group because it satisfies something called as the Lie analysis, and I'll tell you what Lie analysis is. And not only satisfies Lie analysis, but it is also continuous, and it is a symmetric group of the distance function in R2. Now this Lie analysis has something to do with the existence of generators, that's all. So question is, if I give you a group, is it possible to find a generator for that kind of group? So all those groups that have this generator thing with them, and they all fall into the category of Lie groups. That's it. Now the question is, how does the idea of generator arise? So again, the hints are hidden in SO2. So we are going to study SO2 group, and we will find hints that will talk about hints leading to the existence of some objects called as generators. Okay, so we are going to do a step-by-step clever analysis. So let's look at an element of SO2 group. So let us look at R theta. We all know what R theta is, so let me write it down. Cos theta minus sin theta, cos theta. Well, what are the things that you need to remember? Let me write it on the side. You need to remember bit number 1, that if you have a coordinate system x and y, and first you rotate the system by angle phi, so all the x and y's are rotated by angle phi, and then you again rotate all of them by an angle theta, so y is again rotated by angle theta, then you will see that if you apply rotation of phi, first there was phi acting on coordinate, right? So first you have this coordinate, first you will apply phi, and then you have applied theta, then you would see that it is equivalent to you directly apply theta plus phi group on the coordinates x and y. You will get the same thing. So if you multiply them, it is equivalent to you add the angles. From here, I would like to suggest one more idea, that if bit number 2, if there is a particular rotation, and say the rotation happens by an angle theta, but what I will do is I will break this rotation into n different rotations. So each rotation can be denoted by theta by n. and the rotation matrix for each small rotation can be written as r theta by n. So of course, if I apply this r theta by n, how many times should I apply this r theta by n so that I receive r of theta? Well, you have to apply r theta by n times. So you have to multiply them. How many times? So you have to multiply them n times. So when you multiply them n times, the angle this side will get added n times. So theta by n plus dot 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 plus theta by n, and then you'll get theta. So all I want to tell you is that if you multiply a rotational matrix on and act them on coordinates, it's the same as you take a new rotation matrix, which is the addition of the angles that are inside the two rotational matrices that multiply. So this is what you need to remember on a side note. Just keep them on the back of your mind. Now let us come to our rotation matrix and look at a very interesting thing. So if you take theta as very small, so small delta theta, how small? So theta by n such that limit n tends to 0, this small. So infinitesimally small rotations. So if you do infinitely small rotations n times, then you will get the finite.
N tends to infinity.
N tends to infinity. Yes, n tends to infinity. So infinitesimally small rotations, very very small rotations. So you rotate by del theta, then del theta, then del theta, and that way if you rotate it by n times, you will get a complete rotation theta. That means it is quite clear that if I have r of del theta multiplied with r of del theta, and if this multiplication happens n times, then this will nothing but it will give me r of theta. So Lee thought that, okay, so let us look at what happens when I think of small angles. So when I rotate things in a very small way, what happens? Let us look at the mathematical analysis just for fun. So we are going to look at what happens when we are talking about delta theta rotations, that is infinitely small rotations. Well, delta theta is so small that truthfully speaking, delta theta can tend to 0. Okay. Now if delta theta is very very small, then tell me what happens to r of delta theta. So I will have cos of delta theta, and cos of very small angle, that is which is tends to 0, is 1. So let me write them properly. So I'm talking about cos of delta theta minus sine of delta theta and sine of delta theta and cos of delta theta. Then you see that when you're talking about very small infinitesimal rotations, then cos of very small angle is 1 and sine of small angles are the angles themselves. So minus of plus delta theta and 1. Then Lee saw something more interesting. He saw that, okay, so we can write r of delta theta as 1 0 0 1 plus 0 minus delta theta and 0. He said, okay, I can write this further as r of del theta as some identity matrix plus, if I take delta theta common, then I get a matrix that looks like 0, -1 and 1 and 0, and let us name it as X, which is 0, -1, 1, 0. It's a small, it's a matrix. So finally we have R of very small angle is equals to an identity matrix plus the parameter and some matrix X. Well, this is the final result that we have at hand right now. What are we going to do with this result? Well, we are going to do something very interesting with this result. What we will do is the following. We will we know that if I have R of delta theta and I multiply with R of delta theta, and I need to multiply this n times, then it is equal to R of all the delta theta getting added n times, which is nothing but R of theta. So finite rotation is a big multiplication of the infinitesimal rotational matrices. This can be written as identity matrix plus parameter delta theta X. Of course, it is nothing but to the power n is equals to R of theta. That implies, so R of theta, now if you look at this thing, which is 1 plus delta theta X to the power n, if you binomial expand it, then what you'll get? You'll get some k is equals to 0 to n, and capital N and k, and delta theta X to the power k. I hope I am correct. That implies, which is very simple mathematics, nothing interesting here. And always when I write delta theta, you can think of delta theta as theta divided by n, with limit n tends to infinity, whatever. If you look at this expansion, I see that for n tends to infinity, you are going to get the following thing. So for n tends to infinity, you are going to get objects like identity plus delta theta X plus okay. So we have this n, and this n is trapped here. Remember, this is nothing but theta by n. So when you do the combination stuff, the n that would appear above will get cancelled by the n which is below. So, and hence I'm writing the final result. You can do the calculation yourself. I'm just writing out the final results. So we'll get identity plus theta X plus theta square by 2 factorial X square plus theta cube by 3 factorial X cube plus dot. And this was quite amazing, because we know what this series leads to. It is nothing but exponential to the power some parameter theta and some matrix X. Now this was quite interesting. This is brilliant. The simple mathematics, it leads to the idea of writing a matrix in the form of exponential, and this X that appears in the exponential is called as the generator. Now you would say, okay, we went from top to down, but can you prove that if I have e to the power theta X, I am going to get the Lie group? Can you prove it? I'll say, okay, let me prove it. So we go to the next page and prove the whole idea. So what I need to prove that though mathematically I came from r of theta, and r of theta, as you all know, is nothing but cos theta minus sine theta, and just a minute, and sine theta and cos theta. We all know this, and by simple mathematics and some trivial ideas, it turns out that the whole thing can be written as e to the power theta, and we have a matrix. Instead of x, I better write the matrix, which is 0, minus 1, 1, 0. Now the question is, let's go backward. Is it possible that we start from here and we really end up with this kind of matrix? So let's start. So this is nothing but e to the power theta x, that equals 1 plus x theta plus theta square by 2 factorial x square plus theta cube by 3 factorial x cube, and so on. So we know what x is. X is 0, minus 1, 1, 0. Now when you multiply x with itself, when you try find out minus x, x square, you'll get minus 1, 0, 0, minus 1. Just give a check. I hope these are correct, which is nothing but minus 1 taken common. I think you get 1, 0, 0, 1. So you get actually a minus of identity matrix. So x square is that. Similarly, if you calculate x cube, you would find that it is nothing but x square into x, but x square is the minus identity, so it turns out to be minus x. So all these things, if you plug it in, so what happens? It happens that e to the power theta x turns out to be 1 plus x theta. Square is negative, so minus theta square by 2 factorial. Well, you should remember that this is identity, okay, and if there is nothing, then there is identity, so that these are all, each element is a 2 cross 2 matrix. So minus theta cube by 3 factorial x plus theta 4 by 4 factorial. There is nothing, so I think there is identity, dot 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 dot. Now what we will do is we have everything at our hands, and I would like to separate out things in the following way. So that equals, what if I keep identity here and theta square by 2 factorial here plus theta 4 by 4 factorial here plus dot dot dot, and then I separate x theta minus theta cube by 3 factorial x and plus or minus dot 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 dot, whatever. And if you look at this carefully, and if you as I said, there is identity here, there is identity here, so don't because every element here is a matrix and theta square by 2 is just a parameter. So if I take all the identity identity matrix outside, so I get identity if taken outside, then inside whatever the series will remain, which is 1 minus theta square by 2 factorial plus theta 4 by 4 factorial, this will all lead to cos theta. And remember, this is a 2 cross 2 matrix, so always keep track of that. This is a very simple thing. And it turns out the second one, if I take x common from everyone, because x is also a 2 cross 2 matrix, and then I get a sine theta. And let us write them explicitly. So it is 1 0 0 1 multiplied with cos theta, and this is 0 minus 1 1 0 multiplied with sine theta, and we get what we were searching for. It was not so difficult. Turns out this is nothing but cos theta minus sine theta, cos theta. Brilliant, right? Simply brilliant. So the whole idea of Lie group talks about existence of this x. So some x exists. Now for SO2, the x turns out to be 0, -1, 1, 0, but the x can be anything. So for a given anything x, is it possible that when I have some parameter multiplied with x, I get some group, some element of the group, and then if these two are satisfied, and then this forms a group, then I would say that T of theta is a Lie group, and the generator of T of theta, so let me put x prime, and the generator of T of theta is x prime. So this is the whole idea behind Lie group. So given a particular finite group, which is Lie group, if it is a Lie group, it is possible to write it in terms of exponential to the power some parameter and a matrix. That matrix which is on the top of exponential, it has a special name and it is called as the generator. So whenever I write e to the power theta x, this has a special name. It is called as the generator of the group because it actually generates the group when you make the infinite sum and separate it out accordingly. And hence, after all the hard work, you end up with a finite matrix, which finite matrix and the set of all such matrices, they form the group. And in that case, in our case, we actually turned to SO2 group, whose generator turned out to be 0, -1, 1, 0. That's the whole idea of Lie group. That's it. We finished Lie group here actually. That's the whole idea. Any doubt?
Yeah. Here this generator is antisymmetric, right?
Generator here seems antisymmetric, yes.
Yeah. So can you say that okay, generators should always be antisymmetric, or is there, or it is not necessary?
No, it is not. Maybe not necessary. Let me think.
I think generators should be antisymmetric, sir. I mean for this Lie group, or rotation group, all kind of.
For rotation, but if we come to say, remember we talked about Lorentz group, right? RENTZ. So when we talked about a Lorentz group, the elements of Lorentz group, they have this interesting form: cos hyperbolic theta, minus sine hyperbolic theta, again minus sine hyperbolic theta, and cos hyperbolic theta. It turns out the generator, let me write L just to define the generator of this Lorentz group. It turns out to be 0, -1, -1, 0. It seems like a symmetric, right? So, Vikram.
Yes, sir.
So we have this Lorentz group in Minkowski space, which is also a rotation, and it turns out to be symmetric. So you have symmetric generator for Minkowski space rotations, and you have this antisymmetric generator for SO2, which is rotations in the real Euclidean space R2. So question is, when we talk about SO3, then of course the generators must be 3 × 3 because SO3 group elements are 3 × 3, and hence we have to check out whether the generators of SO3 are symmetric or antisymmetric.
Antisymmetric, sir.
It's antisymmetric, right?
Yes.
Okay.
Antisymmetric.
Okay. Okay. So
and we will get 3 generators there.
Yes, we'll get 3 generators. Yes. So You say that even if I consider SO2, SO3, SO4, whatever, every generator for the rotation turns out to be, you say, antisymmetric, right?
Yes, sir.
Okay, okay, that's a generalized idea that you have given here. Now, in the next class, I think we will look at some of the groups and their generators, and then in the next class we will move to Lie algebra, and I think that will be one sufficient course. And then in the next
Hello.
Hello.